Thomas is joining us from Airbus.
Can you hear me, guys?
Yep. Yeah, we got you.
I just have to. Oh yeah. Okay. I can show my screen.
Sweet.
I'm hoping you see my slides.
Yep, we see them full screen.
Okay, cool. Okay, let's go then. So hi, I'm Thomas from Toulouse. I've been working in Airbus Geo, and today I'm going to talk to you about the cloud creation tool called Cogger that we've released as open source. So it's hosted on GitHub, fully open source with an Apache license. We built Cogger because GDAL's native COG support got much better in the last years, but still sometimes lacks some flexibility when you need to really fine-tune what you're going to be putting inside your COGs. So Cogger is actually meant to be used as the final step to create a COG once you've used all the classical GDAL geotiff tools to create the actual image data. It's written in Go, so it's available as a static binaries for all major platforms, and also available through its golang API. And finally, it's a tool that we use daily in production. It's already produced petabytes of data on our cloud platform. So the essence of Cogger is to just the observation that if you're starting from a tiled geotiff with already the desired compression and overviews, then creating a COG from that data is just a byte shuffling operation. It just means take the IFDs that may be found sparsely across the file and move them to the beginning of the file, then recompute the offsets of the actual tile data that's inside the file, so that they'll point to the correct locations inside the new file, and then just copy over that tile data to the new file. While you're doing those operations, you can also do some additional like kind of processing. So automatically switch to classical decompression depending on the size of the created file, so you don't have to ask yourself, oh, should I be starting with a decompression or a classic diff? No, just always create a decompression, and then just Cogger will switch it back to a classic diff if it's less than 40 bytes. We also add the GDAL optimized ghost areas to speed up reading when GDAL is doing the reading. And we're able to read the IFDs and the data from the multiple files, not just a single diff file. And also from that, the output data we stream directly from as soon as we start streaming the first byte, we know the structure. So that means that the output of Cogger can be directly pushed to a cloud storage bucket without having to be stored intermediately on your local file system. So a few usage examples of how you could use that. So this is just the real basic example. The first test is creating a COG file with GDAL. Nothing fancy. SW compressions, you see 18 seconds, 1 minute 12 of CPU. And the second box is how you do that with Cogger. So it's a bit more steps. You first create the full resolution data, then you compute the overviews, and then you use Cogger to rewrite your file to a geotiff file. The full processing time isn't really that different. If you look at the CPU time, we've divided it by 2 already. But this is not really the most useful examples of Cogger. I'll come into that now. We can create a COG file if you have a TIFF file and external overviews. It's the same thing. It will just read the bits from the main resolution, read the bits from the overviews, and stack them all together into a valid COG file at the end. Some kind of advanced usage is if you want to hand make your own overviews. For example, if you need to tweak, apply different compression settings to different overview levels, or if you even want to mix multiple data sources. For example, if in your overview you want to add radiometrically adjusted data so that the overviews seem more or less different than the surrounding neighbors, that's something you can do with the Cogger. So you first create the full resolution image, and then you manually create the overview. So basically each time, starting from the previous one, applying 50% size reduction and creating a new diff from that. And at the end, you just ask Cogger to create that COG file from the full resolution files and the whole list of overviews that you've created. This is just a small example of the golang MPI, which is really, really simple, and it shows here how you'd use that to directly upload your resulting COG file to cloud storage. So you create your storage client, you just open your diff file that's tiled with overviews, you open a handle to the object on the object store that you want to upload to, and just run cogger.rewrite. It will handle streaming that data up to the cloud storage, and it's then up to you to close the others and handle any network or cloud errors that might have happened. And finally, something that's rather exciting performance-wise is that we've often seen that on large images, the overview creation time can be very, very long and doesn't use all the CPUs on the machine. Actually, what we can do is use Cogger to create in parallel multiple COG files. For example, if you have a 10,000 image file, you can create tiles of 4,000 by 4,000. Send each of those tiles to a specific CPU. Do the same thing for the overviews, and then just do the recomposition of all those tiles here. And now you see on these examples here, we've cut down the processing time compared to the normal COG creation by half, from 8 seconds to 15. Into the CPU time. So that's all for me. If you head over to GitHub if you want to try it out, report any issues, collaborate, and I'll try to hang out a little bit in the chat if there are any other questions. Thank you.
Awesome. Thank you, Thomas. Sorry, I was typing without muting. Sorry about that. I try to figure out where to do next. Do you want to stop your share?